Hello everyone, I am Dr.B.Krishnaveni, working as an assistant professor in the Department of Mathematics, Aditya University. In today's lecture, we are going to discuss about eigenvalues and eigenvectors and how to find geometric and algebraic multiplicities. So, for this lecture, these are the learning outcomes. At the end of the lecture, student will able to find eigenvalues, eigenvectors. Similarly, the student are able to find what is algebraic and geometric multiplicity of the given matrix. So, now let us define what are eigenvalues and eigenvectors. If we consider any square matrix of order n, that is A be a matrix of order n by n, and we call lambda, which is a scalar, is called an eigenvalue of A if there exists a non-zero vector x in R power n such that Ax is equal to lambda x. The vector x is called eigenvector corresponding to lambda. Here, the two definitions we are getting, those are eigenvalue and eigenvector. So, first, what meant by an eigenvector? It is a scalar lambda. We call it as an eigenvalue if there exists a non-zero vector x in R power n such that it satisfies the condition Ax is equal to lambda x. And here x is a non-zero vector and that vector x is called eigenvector corresponding to the eigenvalue lambda. So, now let us take n by n matrix with eigenvalue lambda and its corresponding vector is eigenvector, that is x. So, since it is an eigenvalue for the given matrix A, so hence it satisfies the condition Ax is equal to lambda x. From this equation, we can write it as Ax is equal to lambda x. Further, it can be written as A minus lambda In of x. So, here In representing identity matrix of order n since we are taking a matrix of order n. And it is clearly the equation, this equation representing a homogeneous system. And we all know that it has a non-zero solution if the det of that matrix, that is A minus lambda In is equal to 0. Or otherwise, the system has zero solution. Why we are calling this as non-zero solution? So, we call lambda is an eigenvector if there exists a non-zero vector x which is an eigenvector. So, that is what this system must have non-zero solution. It has non-zero solution whenever this condition holds. What that condition is? Det A minus lambda In is equal to 0. And we call this det A minus lambda In is the characteristic polynomial. And the equation det of A minus lambda In is equal to 0 is called characteristic equation of A. Now, the roots of this characteristic equation are known as eigenvalues. Eigenvalues are also called as latent values or proper values. So, here we have gone with the definitions of eigenvalue and eigenvector. So, we call lambda is an eigenvalue whenever there exists a non-zero vector x such that Ax is equal to lambda x. Here in this, lambda is called eigenvalue and x is called eigenvector, that nothing but it is a non-zero vector. Now, by using the definition, we have derived a homogeneous system and this system possesses non-zero solution whenever det A minus lambda In is equal to 0. And we call this polynomial is characteristic polynomial and the equation is characteristic equation. And the roots of the characteristic equation are called eigenvalues, latent values or proper values. So, that means we will get by taking a characteristic equation, we will get equation in lambda. And on solving that, we will get lambda values which we call it as roots of this characteristic equation, which are nothing but eigenvalues. So, now we will see how to find eigenvalues. What is the working rule for that? To find eigenvalues and eigenvectors of a matrix, first need to consider det of A minus lambda I is equal to 0. Since the determinant must have non-trivial solution. So hence we will take a det of that value is equal to 0. This equation is called characteristic equation and whose values are eigenvalues, whose roots. So once we found eigenvalues, we can find corresponding eigenvectors by solving this system. By means of the definition, we got this system. So once you got eigenvalue, substitute here and we'll get the system which is homogeneous system, and solving this will get x, that representing eigenvector corresponding to that eigenvalue. So let us discuss this by taking an example. The question is, find the eigenvalues and eigenvectors of the matrix A is equal to -4, -6, 3, 5. So very first step is we need to consider characteristic equation of A given by det A minus lambda is equal to 0. So here A is of order 2 by 2. So that means what the characteristic A minus lambda I will be, here I is an identity matrix of order 2. So first let's find out A minus lambda I2, that is equal to A matrix, it is -4, -6, 3, 5 minus lambda into I2, 1, 0, 0, 1. On simplification, you got this matrix -4 minus lambda, -6, 3, 5 minus lambda. So now need to get a characteristic equation, that is det of this matrix must be equal to 0. So first let's find what is the determinant of this matrix. Since it is a 2 by 2 matrix and we know that det is nothing but -4 minus a lambda into 5 minus lambda minus of -6 into 3, which is 18. So on simplification, you got the polynomial lambda square minus lambda minus 2, that we call it as a characteristic polynomial. If we equate is equal to 0, call it as characteristic equation. Now need to solve this equation to get the roots, and we call those roots are eigenvalues. On solving, we got the values are -2 and -1. So hence the eigenvalues of the given matrix A are given by -2 and -1. Now need to find out corresponding eigenvectors by using A minus lambda I2 of x is equal to 0. Now for each eigenvalue, we need to find out eigenvector. So now it is noted that many eigenvectors corresponding to each eigenvalue. So now let us consider the first eigenvalue and corresponding, what will be the corresponding eigenvectors. So now by taking the system A minus 2i of x is equal to 0. So here lambda, on substituting lambda is equal to 2, this will be the system. And now what is A minus 2i? Need to find out, that will be equal to -6 -6, 3, 3 of x. So since it is a 2 by 2 matrix, the eigenvector will be column x1, x2 equal to 0. This is the system which is homogeneous. So now you can solve this system directly. This lead to the system of equations -6x1 plus -6x2 is equal to 0. 3x1 plus 3x2 is equal to 0, which gives rise to x1 is equal to -x2. Therefore, let us consider x2 is equal to r be any scalar. So by means of this equation, what is x1 is equal to? X1 is equal to -x2, and we have taken x2 is equal to r. So hence x1 is equal to -r. So therefore, we got the solution x1 is equal to -r, x2 is equal to r, where r is a scalar. So hence, what is an eigenvector corresponding to lambda is equal to 2 is given by v1, let us represent that with v1, is equal to x1, x2, that is equal to -r, r, that can be written as r into -1, 1. So this is an eigenvector corresponding to the eigenvalue lambda is equal to 2. Similarly, we need to find out the eigenvector corresponding to lambda is equal to -1. Now let us assume same. Let x is equal to x1, x2 be the eigenvector corresponding to the second eigenvalue, that is lambda is equal to -1. And we know that the system is A minus lambda I of x is equal to 0. Now by taking lambda is equal to -1, this will become a plus I of x is equal to 0. So, which is given rise to this a plus I. I am performing a plus I. The matrix becomes minus 3 minus 6 3 6. X is x1 x2 is equal to 0. So, this leads to the system of equation minus 3x1 minus 6x2 is equal to 0. 3x1 plus 6x2 is equal to 0, which gives rise to x1 is equal to 2x1. So, now again let us take x2 is equal to r, where r is some scalar. Then what is x1 will be equal to? As from this equation, x1 is equal to 2x2. So, which is equal to 2r. So, hence x1 is equal to 2r, x2 is equal to r, where r is a scalar. So, therefore, what is the eigenvector? Let represent it with v2, that is x1 x2, that is given by r into 2 1. So, this representing an eigenvector corresponding to lambda is equal to minus 1. So, this is the way to find out eigenvalues and eigenvectors. This you can take as practice, by which you can find out eigenvalues and eigenvectors. Next is algebraic and geometric multiplicity. So, first we will discuss about algebraic multiplicity of an eigenvalue. Let us represent that with m lambda. So, the order of an eigenvalue is called its algebraic multiplicity by lambda. For example, if the eigenvalues of the matrix are 1, 1, 2, then the algebraic multiplicity of lambda is equal to 1 is m lambda is equal to 1, that is equal to 2. That means number of times lambda 1 is equal to 1 is repeated. That we call it as algebraic multiplicity. So, in simple we call algebraic multiplicity is nothing but the eigenvalue, how many times it is repeated, that value we call it as algebraic multiplicity. Here the eigenvalue 1 is repeated 2 times. So, hence we call 2 is the algebraic multiplicity of 1. And if you see, we can find algebraic multiplicity of 2 also, that is m lambda is equal to 2. How many times it is repeated? Only once. So, hence the algebraic multiplicity is 1. Next is geometric multiplicity. So, here what meant by geometric multiplicity means the number of linearly independent eigenvectors for an eigenvalue is called its geometric multiplicity and is denoted by m lambda. Capital M lambda is algebraic multiplicity, small m lambda is geometric multiplicity. So, here you can see algebraic multiplicity is nothing but the eigenvalue, how many times it is repeated, that value is the algebraic multiplicity, and the number of linearly independent eigenvector corresponding to any eigenvalue, that number is called geometric multiplicity. Now, what the relation between m lambda and m lambda, that is geometric multiplicity and algebraic multiplicity. Here the geometric multiplicity of an eigenvalue cannot exceed its algebraic multiplicity. For example, if lambda is equal to, you can see the previous example only. Here we got the eigenvalues 1, 1, 2. That means lambda is equal to 1. For lambda is equal to 1, algebraic multiplicity capital M lambda is equal to 2. Then what will be the geometric multiplicity? Either it may be equal to 2 or less than 2. So, that the relation between algebraic multiplicity and geometric multiplicity. Now, let us see this. Now, we have taken another question, finding eigenvalues and eigenvectors only. By means of that, while calculating this question, we can get also what is algebraic and geometric multiplicity. So, first let us consider a matrix of order 3. So, since it is of order 3, what is A minus lambda I will be here? We need to consider I be the matrix of order 3, that is I3. On doing this, that A minus lambda I and the determinant of that matrix is equal to 0, we got this. That is a det of 2 minus lambda minus 2, 2, 1, 1 minus lambda 1, 1, 3 minus 1 minus lambda is equal to 0. So, this we call it as characteristic equation. So, now need to find out the roots of this equation. In order to find out roots of this equation, first of all need to find out the determinant of this matrix. For that, we need to use this formula. This formula is used to find out the determinant of the matrix, that is 3 by 3 matrix. So here you can see the formula. What the formula is including is lambda cube minus trace of A into lambda square. That means we need to find out trace of A. Next, minus of A11 plus A22 plus A33. So means here we need to find out a minor of A11, minor of A22, minor of A33. Their summation into lambda minus det A is equal to 0. Directly you can use this and can find out the characteristic equation, so that the given matrix should be of order 3. Then only we have to use that formula. So for that, first we need a trace. So trace is nothing but sum of the diagonal elements of A. 2 plus 1 minus 1, that is equal to 2. Next, we need to find out the minor of A11, A22, A33. So here it is A. For that, we need the first find out the minor of 2, that is A11 element. So delete this row, this column, det of the remaining elements, which is given by 1, 1, 3 minus 1. Here it is. On finding the determinant, we got the value as minus 4. Similarly, for A22 element, fix this, delete this row, this column, det of remaining elements, 2, 2, 1 minus 1. Determinant is equal to minus 4. Similarly, A3, minor of A33. So now fix this, minor of A33, fix this. Then remaining elements, the determinant, that is equal to 4. So now in the formula we also need det of A, 3 by 3 matrix determinant. We calculated and we got the value is equal to minus 8. Now what the characteristic equation of A is given by lambda cube minus trace of A into lambda square, minor of A11 plus minor of A22 plus minor of A33 into lambda minus det A is equal to 0. On substituting all the values, lambda cube minus a trace value is 2 lambda square plus sum of all the minus. So what are the minus we got is, on adding all this, you got is equal to minus 4. So hence the coefficient of lambda is equal to minus 4 and det value is 8. Here it is. Now on solving this equation, we got lambda values 2, 2 minus 2, which we call it as eigenvalues of A. Now need to find out eigenvectors for each eigenvalue. So let us consider first eigenvalue, that is lambda is equal to 2. By means of A minus lambda is equal to 0, by substituting 2, we got the equation A minus 2A of x is equal to 0. So here x, since A is 3 by 3 matrix, we will consider the eigenvector will be a column matrix. Let us take it as x, y, z. On doing A minus 2I, we got the matrix 0, minus 2, 2, 1, minus 1, 1, 1, 3, minus 3, x, x, y, z is equal to 0, 0, 0. Now need to solve this system to get x, y, z values. For that, we reduced into echelon form. So in order to do that, we can apply this operation. So let us fix this and make down, beside element down 0 means the operation is R3 minus R2. On doing this, we got this system. Next is, we have fixed this and make down 0. So for the operation is, we got this system. And from above matrix, the reduced system we got is minus 2y plus 2z is equal to 0 and x minus y plus z is equal to 0. Now, out of 3, if you fix 1 as one arbitrary constant, then you can find out the remaining values. Let's take z is equal to k. Now, by using this equation, we got y is equal to k. Now, by using x minus y plus k, we got x is equal to 0. So, therefore, what is an eigenvector corresponding to the first eigenvalue, that is lambda is equal to 2 is given by x, y, z, that is equal to x0, yk, zk, that is equal to k into 0, 1, 1. So, therefore, the eigenvector 0, 1, 1 is the eigenvector corresponding to the eigenvalue lambda is equal to 2. Similarly, you can find out the eigenvector corresponding to the eigenvalue lambda is equal to minus 2. Now, by using the system A minus lambda A of x is equal to 0, substituting lambda is equal to minus 2, we got A plus 2A of x is equal to 0. A plus 2A is nothing but 4 minus 2, 2, 1, 3, 1, 1, 3, 1. Let us take x be the eigenvector that represented by x, y, z is equal to 0, 0, 0. So, now reduce this into echelon form, fix this and make down elements as zeros. For that, the operations are given by R2 as 4R2 minus R1, R3 as 4R3 minus R1. And doing this, we got the system 4 minus 2, 2, 0, 14, 2, 0, 14, 2, x, y, z is equal to 0, 0, 0. So, now use the operation, fix this and make down 0. So, simple operation we can use R3 minus 2R2. On doing this, we got the system. Now, after reducing this, we will get the system in this form, that is 4x minus 2y plus a 2z is equal to 0, 0x plus 14y plus 2z is equal to 0, and from the third row already 0, there is nothing to find. Now, again fix any out of 3 variables, one as arbitrary constant, let us consider z is equal to k. On simplification, you got using this equation y is equal to minus k by 7, and by using this equation we got x is equal to 4 by 7 k. So, therefore, what is an eigenvector corresponding to lambda is equal to 2 is 4 minus 1, 7. So, now you can see what is algebraic multiplicity and what is geometric multiplicity. For eigenvalue lambda is equal to 2. So, once you observe here, for lambda is equal to 2, repeated how many times? 2 times. So, algebraic multiplicity is 2, and for lambda is equal to 2, how many eigenvectors we got? Only 1. That means geometric multiplicity is equal to 1. So, therefore, for an eigenvalue lambda is equal to 2, algebraic multiplicity is 2 and geometric multiplicity is equal to 1. In this way, we can find out algebraic multiplicity and geometric multiplicity. Now, one more example you can see in which already calculated what are eigenvalues and eigenvectors. Here, given matrices 2, 1, 0, 0, 2, 0, 0, 0, 2. For that characteristic equation, A minus det of A minus lambda is equal to 0. On doing this, we got the equation lambda minus 2 whole cube is equal to 0. And it is clearly that what are the roots of this equation will be 2, 2, 2. So, what is algebraic multiplicity? Capital M lambda. Repeated how many times? 3 times. So, that is equal to 3. And for lambda is equal to 2, what are the eigenvectors we got are 2 eigenvectors. So, hence geometric multiplicity is equal to 2. So, in this lecture, what we have discussed is how to find eigenvalues and eigenvectors. Similarly, from that, what is meant by algebraic multiplicity and geometric multiplicity. Finally, after calculating eigenvalues and eigenvectors, how to get algebraic multiplicity and geometric multiplicity. Thank you.